Welcome to another episode of Terry's Notes, and today we are going to be looking at acids and bases. An acid is a substance that produces H+ ions in aqueous solution. Okay, so you need to be able to give a definition for an acid. So it's simply a substance that produces H+ ions in aqueous solution, and an H+ ion is essentially a proton. Alright, because hydrogen is 1, 1, mass number is 1, atomic number 1, which means we have 1 electron present, and we have 1 proton present, and we have 0 neutrons. Therefore, if we have an H+ ion, it means that the hydrogen atom has lost an electron. So what we are left with is 1 proton. So that is why sometimes we see an acid being defined as a proton donor. Some basic properties of an acid: they have a sour taste, they turn blue litmus red. Litmus is an indicator. Acids are corrosive, and they also conduct electricity. Alright, so these are just some basic properties of acids. Those of you who've ever tasted an orange or a lime, it tastes acidic, right? It has a sour taste, and so right, okay. And acid anhydride. The word anhydrous means without water. Okay, so once we see the word anhydrous, it means without water. Pure anhydrous acids are composed of covalent molecules, and pure anhydrous acids can be either solid, a liquid, or a gas. In the case of a solid, an example is citric acid. Another example is ascorbic acid, which is really vitamin C. An example of an anhydrous liquid acid is nitric acid and phosphoric acid. In the case of a gas, the examples are sulfur dioxide and nitrogen dioxide. An acid anhydride is an acidic oxide of a nonmetal which reacts with water to form an acid. So we just need to be able to give a definition for an acid anhydride. So we said anhydrous means without water. So an acid anhydride is an acidic oxide of a non-metal which reacts with water to form an acid. Now, what is a base? A base is a substance which will react with an acid to form a salt and water only. Okay? That is a definition that you need to learn. An example of a base is ammonia. Another example would be metal oxides and hydroxides. For example, magnesium oxide is a base, copper 2 hydroxide is a base. So most metal oxides and hydroxides are bases. So we have something called an alkali. An alkali is a base that is soluble in water. An alkali produces OH- in aqueous solution. Now remember, an acid produces H+ ions. In the case of an alkali, it produces OH- ions in aqueous solution. Examples: if we take sodium hydroxide solid and react it with water or dissolve it in water, we end up with Na+ ions and OH- ions. So therefore we see that we have OH- ions being produced. If we take sodium oxide and react it with water, we get sodium ions and we get OH- ions again. In the case of ammonia, ammonia plus water produces NH4+ ions, which is the ammonium ion, and OH- ions. So we notice in all of these we are producing OH- ions. So an alkali is simply a base that is soluble in water. Okay, now we already said that an alkali is a substance that produces OH minus ions in aqueous solution. Some basic properties. Alkalis have a bitter taste. They turn red litmus blue. Right? This is the reverse of an acid. Remember, an acid turns blue litmus red. Okay. Alkalis are also corrosive. They also conduct electricity like an acid. And they feel soapy between your fingers. Right? If you take sodium hydroxide and you touch it, basically the alkali reacts with the oils in your fingers to form soap. And that's why it's feeling soapy. Alkalis react with ammonium salts to produce a salt, water, and ammonia gas. Okay, now this reaction here, you need to know it. It's a typical reaction used to produce ammonia gas in the lab. So we have an ammonium salt, in this case, which is ammonium chloride, and we are reacting it with an alkali, which is calcium hydroxide. And what we are producing is ammonia gas, water, and a salt, which is calcium chloride. Now the drying agent for ammonia is calcium oxide, right? And it is collected via the downward displacement of air. Now ammonia gas is very volatile, meaning that it can evaporate very easily. So, basically ammonia gas is collected like this, right? So we say downward displacement of air. We have ammonia gas moving into the container and it's pushing air downwards. All right. Okay, I have a diagram here showing a typical reaction. So we have calcium hydroxide and ammonium chloride. We heat it, and we have, remember we said ammonia gas is being produced. So the ammonia gas will enter through here and it'll pass through the drying agent, which is calcium oxide, and we collect ammonia inside this cylinder here. Alright, so we have ammonia gas here. So we need to know what do we mix to get the ammonia gas, that is calcium hydroxide and ammonium chloride. We also need to be able to write that equation. We need to know the drying agent, which is calcium oxide, and is collected via the downward displacement of air. Okay, we also need to be familiar with the pH scale. The pH of a substance is a measure of the degree of acidity or alkalinity. Now there is actually a formula to calculate pH, a mathematical formula, but you are not required to know this at this stage. And the scale ranges from 0 to 14. If we have a pH of 7, then we say that the solution is neutral. If the pH is greater than 7, then the solution is alkaline. And if the pH is less than 7, the solution is acidic. Okay. Now, how do we measure acidity or alkalinity? We basically use an indicator, and there are several indicators that we use in the lab. If we use litmus, we know that blue litmus will turn red if the solution is acidic, and red litmus will turn blue if the solution is alkali. Another indicator is phenolphthalein, which is colorless in the acid but pink in the alkali. We also have methyl orange, which is pink in the acid and yellow in the alkali. And we also have screen methyl orange, which is red in the acid and green in the alkali. Now these indicators are typically used in the lab, so once you do a lot of lab work, you will become familiar with them. Now we have to be able to distinguish between strong acids and weak acids. A strong acid is one that is completely ionized in aqueous solution. Alright, the key word is completely ionized in aqueous solution here. Alright, and strong acids have a pH of around 1. So for example, hydrochloric acid. Hydrochloric acid produces H plus ions and Cl minus ions. It is because of the H plus ions that makes hydrochloric acid acidic. In the case of nitric acid, we produce H plus ions and the NO3 minus ion, or the nitrate ion. Again, we are producing H plus ions. Now, when we say completely ionized, it means that all the HCl molecules in solution are being converted into H plus ions. The reaction is complete. In the case of a weak acid is one that is partially ionized in aqueous solution. And weak acids tend to have a pH of around 3.54. Alright, and an example of a weak acid is ethanoic acid, which is CH3COOH, and it produces the ethanoate ion and H plus ions. Now, the key difference between the reactions on top and the one below is this sign here. This sign tells us that the reaction takes place in both directions. So we have ethanoic acid producing the ethanoate ion and the H plus ion. At the same time, we have the ethanoate ion reacting with the H plus ion to produce ethanoic acid. So the reaction is occurring in both directions, and that is why we say that it is partially ionized in aqueous solution, and this is what makes it a weak acid. In the case of the example with the hydrochloric acid, the reaction does not go in the reverse direction. The basicity of an acid. The basicity of an acid is the number of moles of H plus ions produced per mole of acid. So we have three examples here. We have a monobasic acid, a dibasic acid, and a tribasic acid. In the case of HCl, HCl produces H plus and Cl minus. It produces 1 mole of H plus ions. So 1 mole of HCl produces 1 mole of H plus ions. Therefore, it's a monobasic acid. In the case of sulfuric acid, we have 1 mole of sulfuric acid producing 2 H plus ions and SO4 2 minus ions. So in this case, we are producing 2 moles of H plus ions. Therefore, it's a dibasic acid. In the case of phosphoric acid, we have H3PO4 producing 3H plus PO4 3 minus. Now, we are producing 3 hydrogen ions per mole of phosphoric acid. So therefore, this is a tribasic acid. So whenever they ask you about the basicity of an acid, just write the equation and determine how many moles of H plus ions are being produced per mole of the acid. Okay? We need to understand some reactions with acids and metals. The first reaction is the reaction with metals. Acids, except nitric acid, react with reactive metals, that is iron and above in the reactivity series, to form a salt and hydrogen gas. So acid plus a metal generally produces a salt and hydrogen gas. So we have two examples here. Magnesium plus 2HCl produces MgCl2 plus H2 gas. So hydrogen gas is being produced, and we have a salt being produced, in this case magnesium chloride. In the second example, we have zinc plus sulfuric acid producing zinc sulfate and hydrogen gas. So again, we will produce a hydrogen gas and a salt, which is zinc sulfate. Nitric acid is an oxidizing agent. It releases oxides of nitrogen. Nitrogen dioxide and not hydrogen gas is produced when reacted with metals. So for example, if we have iron reacting with nitric acid, we end up with nitrogen dioxide gas instead of hydrogen gas. Okay? And that is because nitric acid is an oxidizing agent. Okay? Now in this equation here, we have Fe2 plus moving to Fe3 plus. An increase in oxidation number is called oxidation. So therefore, the nitric acid is acting as the oxidizing agent. Reaction with bases. Acids react with bases to form a salt and water. Alright, so first example is magnesium hydroxide. Magnesium hydroxide plus hydrochloric acid produces a salt, which is magnesium chloride, and water. So the magnesium comes from here and the chloride comes from here. The other example is copper 2 oxide plus sulfuric acid produces copper 2 sulfate plus water. So in both cases we produce water and a salt, right? Copper comes from here and the sulfate comes from here. So acids plus bases gives you a salt and water. Reactions with carbonates and hydrogen carbonates. Acids react with carbonates and hydrogen carbonates to produce a salt, water, and carbon dioxide. So we have three things being produced here. In this first example, we have calcium carbonate plus hydrochloric acid produces calcium chloride, water, and carbon dioxide. So we have water and carbon dioxide in this case, and a salt. And the salt, we get the calcium from here and the chloride from here. In the case of a hydrogen carbonate, so sodium hydrogen carbonate plus sulfuric acid produces sodium. Sorry, this is a mistake here. It should be sodium sulfate. Alright, producing water and carbon dioxide. Alright, the reaction between barium carbonate and sulfuric acid soon stops because the barium sulfate produced is insoluble. It will coat the barium carbonate and cause the reaction to stop. Now this is a typical examination question here. So if you have a solid piece of barium carbonate, so you have BaCO3, and we want to react it with sulfuric acid. The salt produced is BaSO4, but barium sulfate is insoluble. So what will happen is that it will coat the outside of the barium carbonate and prevent the reaction from taking place further. Acids in everyday life. Now, most of us have had food and ended up with indigestion. We usually take an antacid. An antacid is a substance used to neutralize excess acid in the stomach. So this is just a simple definition for an antacid. Magnesium hydroxide is used for this purpose. Magnesium carbonate and calcium carbonate can also be used. So essentially what is happening is that you are taking a base and trying to neutralize the acid. So magnesium hydroxide plus hydrochloric acid produces magnesium chloride and water. Remember, inside the stomach we have hydrochloric acid. And if we have a buildup of hydrochloric acid, we need to neutralize or reduce the amount of acid in the stomach. In the case of baking powder contains a solid mixture of sodium hydrogen carbonate, which is NaHCO3, and a salt of a weak acid, which is the weak acid in this case is tartaric acid. So sodium hydrogen carbonate plus, now we said a salt of a weak acid. What will happen is that when we mix water to the baking powder, we end up producing H+ ions, and the H+ ions react with the sodium hydrogen carbonate to give us carbon dioxide. So if we take some baking powder and we just add some, let's say, vinegar, you're going to see effervescence, meaning that carbon dioxide is being produced. So in the case of baking powder, we have the H+ ions reacting with sodium hydrogen carbonate, giving us Na+ ions, water, and carbon dioxide. And the carbon dioxide is what we use in cooking. Most of us may be taking vitamins, and we tend to take vitamin C a lot to prevent us from getting sick. And vitamin C is ascorbic acid, and it is required by the body. Ants bites. When certain ants bite you and it stings a lot, And what is happening here is that the ants, they release methanoic acid, which tends to burn. Alright. In our kitchen, we tend to have vinegar, and vinegar is ethanoic acid, and it is used to preserve some foods. And the reason why it is used as a preservative is because the low pH prevents the growth of bacteria. Alright. And we just have to talk about the acid-base properties of some oxides. So in terms of oxides, we have acidic oxides, or acid anhydrides. They dissolve in water to form an acid. So some examples of acidic oxides are sulfur dioxide, sulfur trioxide, carbon dioxide, and nitrogen dioxide. So what we are saying is that any one of these can dissolve in water to produce an acid. So sulfur dioxide plus water produces sulfurous acid, which is H2SO3. Alright. Let's look at basic oxides. Basic oxides are simply oxides of metals. They react with acids to form salt and water. We met this previously. Examples of basic oxides are copper 2 oxide and magnesium oxide. So if we take copper 2 oxide and react it with sulfuric acid, we end up with copper sulfate and water. And we have something called amphoteric oxides. Now they react with both acids and alkalis to form salts. And examples of amphoteric oxides are lead oxide, zinc oxide, and aluminium oxide. Alright. Now students have difficulties remembering some of these equations. Try your best to remember them. So if we look at lead oxide will react with nitric acid to produce lead nitrate and water. So we have an amphoteric oxide plus an acid producing a salt and water. Now if we take the same lead oxide and react it with sodium hydroxide, right, which is an alkali, it produces a salt and water. So in this case, a salt and water is being produced again. If we look at zinc now, if we take zinc oxide and react it with an acid, we get a salt and water. And if we take the same zinc oxide and react it with an alkali like sodium hydroxide, we get a salt and water again. So therefore, amphoteric oxides react with acids and alkalis to produce a salt and water. And the last type of oxide we will be looking at is neutral oxides. They do not react with acids or alkalis. And two examples are carbon monoxide and nitrogen monoxide.